Alright guys, we're doing wavelength. We're doing it right now. Let me fix this thing. There we go. Okay, 1 and 2 and number 3 is super easy. We're going to have a revelation with this one because I'm tired of all the lies on this. Alright, physics teacher attaches a slinky to the wall and begins introducing pulses with different amplitude. So that's the height of the wave, right? The baseline to the middle or the baseline to the bottom. Which of these two pulses will take the least amount of time to reach the wall? Well, here's the deal. Amplitude has nothing to do with wave speed. Nothing to do with wave speed. Therefore, they will reach the wall at the same time. That's going to go right here, right? I do want to show you this. Let's look at the key on this one. I don't want to show you this stuff. Now, you may be deceived, so just check this out. The wavelength is the same, so they would reach the wall in the same amount of time. Okay, disregard this. All they do is change the amplitude, right? So let's look at number 2. The physics teacher then begins introducing pulses with different wavelengths. Now we have a different wavelength here. Notice that D is short and C is quite a bit longer. Which of the two pulses will take the least amount of time to reach the wall? So remember our formula for velocity. And we're assuming that if it has a higher velocity, then it's going to reach the wall faster. Well, check it out. It's wavelength times frequency. We know this is wavelength. Well, yeah, the wavelength is higher here, but the frequency is also lower, right? So it's like you raise this and you lower this, so it still should have the same velocity. Whereas this one, the wavelength is smaller, but the frequency will be higher when the wavelength's shorter, which means same velocity. So look at this. Look at this. This is the key, by the way. D has a smaller wavelength, that means that it will move faster and faster and it will reach the wall first. Dude, no, this is a liar key. Because wavelength does not what's the word I'm looking for? Not detect, determine speed. Right? Different mediums it's traveling through will make it take longer or shorter, but wavelength does it just based on the formula. Because most of the time, well, when it happens, if the frequency is higher, the wavelength is lower. These are inverse, right? So in short, these will meet the wall at the same time. Let's look at this. I'm going to drag this over. This is the truth coming. I will bring the truth. Screencast-o-matic. So let's look at the first one. Da-da-da-da-da. This is the first one. This is straight up physics classroom. These links that are probably broken, but you can still get to it. They reach the wall. This is A, number 1. They reach the wall at the same time. Don't be fooled. The amplitude does not affect the speed. They have the same speed. There we go. Okay? Now let's look at B. This lion key try to betray you. They will reach the wall at the same time. The wavelength does not affect the speed at which the wave travels. They will travel at the same speed. The speed of the wave is only altered by the properties in the medium, which mean what it's going through, like air, water, in which it travels through. Therefore, it's going to reach it at the same speed. That was a lying key, and it betrayed many people, but it's not going to betray you. So, with that being said, they reach the wall at the same time. That's the truth. Just like if you look at the emission spectrum, right? You got radio waves, visible light, gamma. You know that visible light, it travels the speed of light, right? Yeah. And so does X-rays and so does gamma rays. That means they all travel at the exact same speed. They just carry different amounts of energy, right? They have a little bit different properties, carry different amounts of energy, but the same speed. So like if I walk towards you, if a car coasted at you at 5 miles an hour and hit you, you're going to feel that impact, right? And if a bike coasted at you at 5 miles an hour, they're both going the same speed, just one is obviously carrying more energy, right? So keep that in mind. That key was a liar, and I brought you the truth. With that being said, let's do the next problem. Alright, so this is actually pretty easy. We're using our formula straight up. This is like the easiest calculations you're going to do. Stan and Anna are conducting a slinky experiment, blah, 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 blah. We got to find speed. Pretty much we got to find velocity, right? Speed, velocity. They give you the wavelength. They give you the frequency. Our formula is right here. We're just plugging stuff in. So wavelength is this little weird symbol here. It looks like a Y-ish. Frequency is the F. So you just do wavelength times frequency. So you can probably do these in less than like literally 2 minutes, but I'll do a few. I got my calculator here. 1.75 times 2, 3.5. And then because it's velocity, we need to put our units, meters per second. That's our units for velocity. And let's just keep going. So 0.9 times 3.9. 0.9 times 3.9. 3.51 meters per second. 1.19 times 2.1. 2.499. Cool. With this one, let's look at this first one. Zinc coil, right? Notice that the first one, the wavelength is 1.75, and the frequency is 2. And the second one, the wavelength almost got cut in half, and the frequency almost got doubled. You see how that is? So 0.9 times 2 is like 1.8, so that's about half, give or take. And then the frequency is almost double. So notice that the speed stayed the same, right? 3.5, 3.51, that's pretty much the same. So when you look at this key, and they say that, well, it reaches the wall first, it's wrong. It doesn't make any sense, right? Because look, if you change the wavelength, the speed is practically the same, right? It doesn't change very much. That's negligible, 0.01. That's not important, right? So just, it reinforces the fact that it doesn't determine the velocity. So let's keep going. We'll do the rest of these. I'm not going to calculate them. I'm just going to write them in because really it's an easy calculation. Just double check your work when you're done. This is, I mean, you're multiplying, so it's pretty much the most basic deal you can do. What is it? 2.5. Bam. Make sure we're putting our units because that's important. You got to put your units. And 2.52 meters per second. Cool. So I'd imagine you didn't have a problem with this. You got the 1 and 2 pretty good. I'm going to pause and see if I'm going to do the next page, or if I'm going to make it another video. Alright, so we're going to do this page. I'm going to do as much as I can. I'm running out of time, but we got to do it. Alright, number 4. The wavelength of a wave in a uniform medium increases. Its speed will blank. This is the same as the previous page. I want to show you this, and then I'm going to show you some stuff on the other page. I might even just do 1 or 2 of these and make a new video for the rest, but we got to go through a few of these. Number 4, the wavelength of a wave in a uniform medium, means the medium's consistent, it's all air, all whatever, its speed will, let's look what they put. They put decrease. Its speed will decrease if the wavelength, what is it? The wavelength of the wave in uniform medium. If the wavelength increases, its speed will decrease. That's what they put in the key, right? Does that make any sense? Let's look. Let's look at our actual notes. I'm going to pull them over here. Let's read. We're going screencast-o-matic. They did an experiment, right? They have a wave generator. Makes waves. The tension is in newtons. That's just like the tightness of the rope. It's just those things that wobbles up and down and makes waves. We have the frequency and we have the wavelength. So, and then the speed is last, the velocity. Notice, so we're keeping the same tension from what we're looking at, so 5 to 1. Look at the wavelength. It increases. Look at the speed. 16.2, 16.4, 16.1, 16.2. It's going to vary a little bit just because it's an experiment. It's not a perfect, exact experiment, but it's the freaking same velocity, man. It's the same. So that's not true. It's not decreases. It's literally the same, right? And let's scroll down a little bit more. There we go. The lesson of this lab activity described above is that wave speed depends upon the medium which the wave is moving. Only an alteration in the properties of the medium will cause a change in speed, right? What it's going through, right? If you go from like air to water to air or something like that, yeah, the speed might change. It might take a little longer path. Otherwise, that doesn't matter. They did mention here, and read this, you should, it's good, like, you know, when the rope was tighter, the wave went through a little bit faster. But again, that's not the wave itself. That's the properties of the experiment that we're doing. The properties of the rope is changing the speed, not necessarily the wave, right? Because again, if we look down here, these numbers are pretty consistent. the wavelength gets a little higher, it stays pretty consistent. The average is 25.6. So we have 25.6, 25.7, 25.1. So the average is here. That's pretty good. It's pretty precise, I'd say, right? Most of these are pretty precise. So that is a lying key, you know, potentially made by a liar. I don't know. I don't know the person. Who knows how long it's been here, but many have been deceived. So it is remain the same. As the wavelength of a wave in uniform medium increases, the frequency, okay, so this is a little different. So as the wavelength goes up, so if we have this, oh, let me move my deal so you can see it. As the wavelength increases, now this will change. If the wavelength goes from this to this, well, yeah, the frequency is going to go down. So the wavelength increases, the frequency will decrease. Now that makes sense. So we're good on that one. That would make sense. Just the speed ones are a little bit off. All right, number 6. The speed of a wave depends upon, is causally affected by, okay, the properties of the medium right here. A, perfect. Frequency, no. And see, look. And now we're back to this. See, now we're saying A, the property. So this contradicts 4 and 5, right? But we know that it is A, right? Because if they said, yo, the wavelength does matter here, and all of a sudden here they're saying it doesn't, that doesn't make no sense. The speed of the wave depends upon the properties of the medium, right? The air. Is the air hot? Is it cold? Is it windy? I mean, those little things do make a difference, especially like hot air, because the air will expand, contract, whatever. All right, let's look at number 7. A water gun fires 5 squirts per second. The speed of the squirts is 15 meters per second. So let's, before we do anything, we always write our stuff down. So we have our velocity, which is 15 meters per second. And we have our frequency, which is 5. Oh, let me do this. F equals 5, right? I guess you could say hertz, but I'm just going to say it. How much distance is each consecutive squirt separated by? Well, what's our formula? I'm trying to remember off the top of my head. Velocity equals distance times time. No. I know we're going to do, hurry up and pause. Got to remember this formula. Know how to do it. So we got our velocity is 15 meters per second, and our frequency is 5. So we are going to do the same formula we used on the other page. It's kind of tricky. Oh, I went too far. So velocity equals wavelength times frequency. So velocity equals wavelength times frequency. So our velocity is 15. And our frequency is 5. And our wavelength is here. So in this case, our wavelength is going to be our distance, right? So we're going to divide this 5 out, divide this 5 out. So how much distance is separated? 3 meters. So sometimes it gets a little tricky to remember that in some of these cases, our distance for this formula is just our wavelength. That's more or less our wavelength, right? So what happens to the distance between squirts if the rate of fire is increased? We'll just, think about it normally. Like if you're shooting a gun, a semi-automatic, which means every time you pull the trigger, it shoots. Boom, boom, boom. If I pull the trigger faster, boom, 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 there's going to be less distance between bullets, right? I mean, that makes sense. Same thing with waves. If you go from this frequency to this frequency, well, the wavelength is going to be shorter, which means the distance between waves, or squirts in this case, will go down. So we're just going to put decrease. Cool. So explain how this example is analogous to the relationship between wave frequency and wavelength. Well, we pretty much did that, right? So a high frequency wave, like this one on the left, the wavelength will be shorter. It's inverse relationship, means like opposite relationship. As one goes up, the other goes down. And a low frequency wave, like this one, will have a very wide wavelength, right? So that's the relationship. Pretty straightforward, right? Okay, let's, I'm going to stop here because these other ones are quite a bit more calculations, and we'll finish that up in the next video. All right, guys, if you got any questions, let me know. Rock and roll.